Okay, so in this lesson, we're going to learn about real numbers and the operations that we can perform on them. So first, let's talk about what real numbers are. If you are curious, we will talk about real numbers. At some point, you're going to learn about numbers that are not real. They're called imaginary numbers or complex numbers. But for right now, we're going to focus on real numbers. And you should have learned this before. We can break real numbers into two sets, the rational set and the irrational set. So first, I want to just tell you what the rational set of numbers is here. And so our rational set of numbers is any number that can be written as a fraction. And we'll talk more about changing these forms and what they look like. But these could be things that are fractions to begin with. All right, so this could be like 10 over 7. Or it could be a mixed number, 1 3/4. Or we could have a decimal, 0.32. We could even have repeating decimals, 0.5 repeating, like 0.55555, on and on and on. That counts. We could have negative numbers, so these fractions could be negative. Those are all things that are count in the rational number system. All right. In the integer system, so notice as these are circles within this gets smaller. Just like a Venn diagram, they overlap, but as they get smaller, they're going to get a little bit more specific. So our integer numbers are like what you would think of on a number line. So they go backwards forever. So I've got ... in the beginning, -2, -1, 0, 1, and 2. And the ... on both sides just indicates that this counting pattern goes on forever, negatively and positively. Again, whole numbers is going to zoom in a little bit, and whole numbers is going to cut off the negative part. It's going to start at 0 and count up forever. And then natural numbers, think about if you were asking a child to count something, it's where would they naturally start counting. So those natural numbers are going to start at 1, so they're going to leave 0 off, and then go on and on into infinity. So that's our rational number side. And then our irrational number side, if rational numbers can be written as fractions, then irrational numbers cannot be written as fractions. So irrational numbers, you could maybe make a note for yourself here that they cannot be written as fractions. And there's like 3 good examples of that. Pi is probably the most famous one you know. You may have learned that pi is approximately 3.14, but really pi goes on forever and ever, and it does not repeat in its counting. Even if something has a pattern, so if it says 1.2, 1, 1, 2, 1, 1, 1, 2, this does have some sort of pattern going on, but because the pattern is not specifically repeating, it is not a rational number. And then lastly, non-perfect square roots. So for example, if I try to say the square root of 5, I don't know the square root of 5. Nothing multiplies by itself to give me that, so that's an example of an irrational number. The square root of 4, for example, is 2. And so the square root of 4 would fit really in this natural number category, which means it would also be part of the other sets on this side. So notice that numbers, we've kind of already talked about this, but numbers can be written in various different representations. Not all of them can be written differently, but all rational numbers can be written in these different representations. So some of these representations are fractions, which can be written in lots of different ways, but remember there is improper and mixed numbers. Most of the time when we're doing algebra, this is just a note for you, we want improper fractions. Mixed numbers are better when we're doing word problems. Other than that, we don't generally fool with mixed numbers in algebra because it's harder to solve with them. All right, we can also write things as decimals. A lot of times things can be written as integers, especially if they already are. And then radicals, which for right now is all you know that is as square roots. So just know that there are all these different representations of numbers. All right, so with numbers, the big thing that I want you to think about going forward is we can compare numbers in 2 ways. We can talk about how their size compares to one another, but also how their relationship compares to one another. So for instance, we could talk about if a number was larger or smaller, but we could also talk about if both numbers were positive, if both numbers were negative, if both numbers were rational, so on and so forth. So let's look at a few examples on how to do that. So for this example, they're asking us to put a set of cards in numerical order. So we have 3 numbers, and they're asking us to order these cards from least to greatest. So in this instance, they're asking us to compare the size. So for the sake of your notes, I think that you should be writing down this part of the problem, that you have these three numbers and you are being instructed to compare them and order them from least to greatest. Remember, you can pause the video if you need to do that. All right, so when we compare the size of numbers, the best thing for us to do is to be able to write these numbers in the same format, which is why we just talked about different forms of numbers. In general, the easiest format to compare numbers is to change them all into decimal or decimal approximates. It's a lot easier, I mean, you know that by now, it's a lot easier to compare decimals than it is to compare fractions or other versions. So what we're going to do is change all of these into a similar format. And at this point, the only way that you know how to do that is to change them all into decimals with a calculator. Okay, so some of you might actually have the question of how do I change these to a decimal in my calculator? I think the square root you should be familiar with. You have used calculators that have the square root button. What you haven't done probably as much is figured out how to compare or change numbers if they don't have a fraction button, which these new calculators you will use do not. So it's important that you know that this fraction bar means division. So to change this over, you're going to do 40 divided by 11. And then your calculator will give you this decimal equivalent. Now the calculator in this instance is going to spit out something that looks like 3.636363, and it might even at some point say something like 37, but this is an example of a decimal that is repeating, and that 7 is happening because it's rounding up at the end. All right, so now that we have these fractions in equivalent forms, they're all as decimals, it's a whole lot easier to see which one is the smallest. So notice that the least over here is going to be this 3.2, the square root of 10. What am I saying? The least is going to be this one, 3, and then 3.2, and then 3.63. Your book recommends that you graph this. I'm not really sure that that's actually necessary for you to graph these on a number line, but you could do that so that you could compare them and then order them from least to greatest. So there would be your example, ordering those from least to greatest. All right, so now let's talk about how we compare sets when we're talking more about the relationship between the two numbers. So before that, we need to talk about what some of these definitions are. So we have sets, and a set is a collection of objects. An element is the object itself that's within the set. And subsets are sets that are fit within a greater set. So a smaller section of that set, maybe a more specific section. All right, so the best example I can give you, just kind of real world and not talking about math for a second, would be if we talked about the alphabet. So if we talked about the alphabet itself would be the set. The letters within the alphabet would be the subset. And not the subset, would be the elements. And there's a variety of different subsets that could be within that. So for instance, different subsets that could be within that would be like the vowels, right? That would be a subset. Or you could say the consonants, or you could say A, B, C, D, E is a subset. All of those are subsets within it. All right, so hopefully this helps you understand. A few things that we need to note in general. Sets are noted with these curly brackets. So they have this like curly set within them, and you write the elements within the set. Man, this pen is terrible. Okay. All right, I got that working now. So this is the notation up here. If you can see right beside it, those curly brackets, that's the notation for set. Elements are listed within that. And then subsets are written with like a sideways U. So for instance, saying that the vowels is a subset of the alphabet, this symbol right here means subset. Okay? So we have a few quick examples left. In the set of real numbers from 1 to 10, which elements are in both the subset of even and the subset of multiples of 5. So I'm talking about the set of 1 to 10. So that is my whole set. So if I write that set out, and now I'm also going to list out my even subset. So obviously even numbers can go on forever, but I'm specifically talking about the ones within this set. So notice that I'm going to stop at 10. And then I'm also going to list out my multiples of 5. And those are going to be, again, in this set, 5 and 10. All right, so this question specifically asked me which elements, remember the elements are the numbers, right, the values within, are in both the subsets. So I'm looking in these subsets, and the overlap that I see would be 10. So the only element that actually counts here is 10. So that would be your answer. The answer to which is in both is 10.